So we're going to talk now about types of discontinuities. In other words, what happens if the limit as x goes to c of f of x does not equal f of c? When that happens, we say that x equals c is a point of discontinuity for f of x. And because it is a point of discontinuity, we're interested, can we say something else about the shape of the graph of f near x equals c? And it turns out that we can by using the limit as a tool to figure out the shape. So we're going to use the limit as x goes to c of f of x as a tool to classify the point of discontinuity according to its shape. And there are going to be three basic shapes that we're going to look at. In the wild, there are more than these, but these three cover most of the functions that you will encounter. Probably 95% of the functions that you will encounter. So, the other good news is that we are already familiar with all three shapes, and we're really just going to be putting new names on stuff that we already know. So let's consider now these three shapes. The first possibility is the point of discontinuity. And this occurs if the limit as x goes to c of f of x is equal to some real number L. When the limit as x goes to c of f of x is equal to L, this means that the shape of the graph of f near x equals c has to look like this. It has to come in towards L from the left and come in towards L from the right, because the limit is equal to L, which means the limit from both sides is equal to L. Well, we have seen this shape before. What have we called this before in a graph? We called it a hole. That's exactly right. So the only thing that we're going to do is take that term hole, and now we're going to call it a new and spiffier term, point discontinuity. Yes, sir.
They're the same one.
That's right. They are synonyms for each other. That's right. For some functions, f of c might actually exist, and it might be some point. For other functions, it simply won't exist at all. We don't care. What makes a point discontinuity is that the limit exists, but the limit does not equal the value f of c. If it did, then this blue point right here would move up and fill the hole, and we would be continuous at x equals c. And the classic example of such a function is the function f of x equals sine of x over x. We've seen this one before, and we're going to see it again. Quick question. What are the excluded values for f of x?
0.
X equals 0. So we have an excluded value. Excluded values will automatically be points of discontinuity because my function can't exist at that point. So this is a point of discontinuity, and now if I classify it by taking the limit Then I take the limit as x goes to 0 of sine x over x, and I get what value that everybody knows? 1. Exactly. The function does not exist at 0, but the limit is 1. And that means that the graph of sine x over x near x equals 0 is going to come in, have a hole at x equals 0, y equals 1, and keep going. So we learned something about the shape of the graph around x equals 0 from the limit. The limit is our tool of analysis. Good so far? Good. Well, our second type of discontinuity is also a familiar friend, and that is the asymptotic discontinuity. If the limit as x goes to c of f of x is infinite, meaning any of plus infinity or minus infinity or plus infinity from one side and minus infinity from another, then f of x has an asymptotic discontinuity at x equals 3. Now we've seen this before also, except we called these what? If my limit was infinite. Yeah, true. We called them what kind of asymptotes? Vertical asymptotes, exactly. And the limit was infinite, and that was our clue that the graph had a vertical asymptote here. So, the classic example here is g of x equals 1 over x. And we all know the graph. Here we go. Here we are. And I have an excluded value at x equals 0. And lo and behold, when I take the limit as x goes to 0 of 1 over x, that limit, because of the form, we know it to be infinite. In fact, it is positive infinity from the right and negative infinity from the left, but we don't have to work that hard to classify this as an asymptotic discontinuity. The conclusion that we draw because of our analysis is that G has asymptotic discontinuity at x equals 0. Yes, sir.
But geomax is continuous function.
Good point. You remember. Very nice. That's right. It is continuous because it is continuous at every point in its domain. It also has an asymptotic discontinuity, and that's why that continuous function definition is tricky. Nice. Okay. Well, let's consider a third type of discontinuity, one that we have also seen. If the limit as x goes to c from the left is a value L, but the limit as x goes to c from the right is a different value M, then we're going to, let's think about the shape here. How does that work out? Let me draw a function like that. Here's a C, and here comes F, and it's going to go to some number L from the left. And here it goes from the right, it has a different value M, like that. So it would really have to happen like this, from the left L, from the right M. in order for that to happen, my function has to jump instantaneously from L to M. And so we're going to call this, we're going to say that f of x has a jump discontinuity. At x equals 0. At x equals c, excuse me. There. So this is our third and final classification, where the limit from the left is different from the limit from the right. So just to recap, we have these three types: point, asymptotic, and jump. The characteristic is that the limit exists in the case of the point. The limit is infinite in the case of the asymptotic. And the limit from the left and the limit from the right are different for the jump. I wrote it as limit from right is different from limit from left. So our classic example of a function with a jump discontinuity would be h of x equals x over the absolute value of x. In my other class, somebody asked me, is that 1 times 1? No. It is the absolute value of x. Okay. Now let's explore this function just a little bit. First of all, what are the excluded values of h? X equals 0. So we have a point of discontinuity at x equals 0. And so we consider now the limit as x goes to 0 of x over the absolute value of x. So this is kind of weird. Not really sure here. So let me consider now a value of x that is close to 0. Give me a value of x close to 0. And then possibly not. Good question. Let's make it start with positive. 0.001. Great. Take 0.001. What's the absolute value of that? So what happens when you divide? You get 1. Is that going to happen for every positive number? Yep. Yes. So the limit from the right is positive 1. What happens if I take a negative number? You saw this coming, didn't you? Yeah. Exactly. If I take, for example, negative 0.001, take the absolute value, 0.001, divide, you get negative 1. And that must happen for every negative value. Really, because the absolute value of x is defined as x when x is non-negative, and the opposite of x when x is negative, so that x divided by opposite x must be negative 1. Okay? So because these two limits from left and right are different, I conclude, therefore, that h of x has a jump discontinuity at x equals 0. Just that. What are some other functions that we have seen that can have jump discontinuities? Yes, sir. Yes, into x has a jump discontinuity where? Bingo. At every integer. What other types of functions? You were about to say something. Piecewise defined functions can often have jump discontinuities at the joints where the pieces come together. That's a common phenomenon. Yep. Very good. So those are our three types of discontinuities. And to find them, we look for potential places where our function might have potential problems, excluded values, joints for piecewise functions. And then we use the limit to classify. Let me close off with an example of a piecewise function. Let's consider f of x is equal to x squared plus 1 for x is greater than or equal to 2, and x minus 4 for x less than 2. And the problem it might present is find and classify any points of discontinuity. And we're going to think of this in 3 parts. First, we're going to think of it as examining the first piece for any points of discontinuity. But we know something about that function. What type of function is it? It's a polynomial. And we remember that the polynomial theorem guarantees, oh, look at that. Huh. Polynomial theorem guarantees polynomials are continuous. You didn't know what we were saying that, but that's really what the polynomial theorem is saying. So the piece x squared plus 1 is a continuous function on the entire set of reals. So there are no points of discontinuity on this piece. Then we consider the second piece. And it also is a polynomial, so it also is continuous. Now we consider the joint where the 2 pieces come together. And we need to consider whether or not this function right here has any type of discontinuity. So we need to look at the limit as x goes to 2. But that means we need to look at limits from left to right. And when I look at the limit from the left, I get -6. And when I look at the limit from the right, I get 5. That's right. And this is enough information to conclude that f has a jump discontinuity at x equals 2. And I don't even need to worry about the value of f of 2, because I've already discovered that the limit fails to exist, therefore my function is discontinuous. You guys have a great weekend.
So the limit x goes to 2 is